Hello and welcome to podcast number 42. We're continuing with alkene addition reactions. So, podcast 40 and 41 gave some initial examples of them, got some definitions going. This one's going to delve into a couple things we've already looked at in the previous podcast, and that is hydration reactions, addition of water across a double bond. But we're going to concern ourselves with rearrangement and then, more importantly, come up with reactions where we don't have to worry about rearrangement. And so, just in general, just an overview that you should keep in the back of your mind, carbocations can form anytime there's an acidic environment with an organic molecule. So, acidic environment, just in the simplest perspective of an acid, provides an H plus. When the H plus is involved, if it interacts with the molecule in any way, then a plus charge will be present on that molecule. And that plus charge will most likely end up finding its way to a carbon. And so knowing the relative stability of carbocations, tertiary over secondary and secondary over primary, or resonance over non-resonance, will help you to make good decisions on how a reactant's going to go. And that definitely is going to be part of your experience in alkene chemistry. Okay, so with that, want to go ahead and look at addition reaction with rearrangement. So I want to start with the molecule. Acidic conditions, so I'm using HCl. Again, acidic conditions can often lead to a carbocation being formed, and that's what we're going to get in this case. And the double bond we're choosing is located at the end of the molecule. It's a so-called terminal double bond. Um, there's an asymmetry to the double bond. There's two H's on the right carbon and only one H on the left. So again, keep in mind under acidic conditions, H plus will be the first thing to react with alkene. H goes where H is. It'll go to the side with the more H's, meaning these pi electrons will reach out and grab that H, kicking those electrons to Cl. So it'll do this. Okay, I've drawn this twice. It's an identical thing, but notice the slight difference. This H I'm emphasizing on the lower one, it is still here. There's still an H. So in fact, if I consider this, there's an H here. There's also H's here. There's an H here, but I'm not going to consider the last one because if an H left from a carbocation, you'd have a +2. That would never happen. So we're only going to consider the neighboring H's. If this H moves over, so if this one slides over like it's going to have here, it'll go to tertiary. That's good. If any of these H's, any of these three H's were to move over, you'd be left with a primary carbocation, which would be relatively unstable. So those H's at the terminal end aren't going to slide over. This is the one that has the greatest propensity to slide over. So I'm going to get rid of it and leave it to this one is going to be the one I'm going to focus on rearrangement. This is one I'm not. So the reality is rearrangement is going to be highly probable. Intramolecular reactions are much faster than inter. And so as a consequence, this H can move over long before the Cl can get in. So you can move over to a neighbor before a Cl can swim through solution, loop around, do whatever it has to do, and attack. So the likelihood of having secondary carbocation is highly reduced. It's going to rearrange at tertiary. You will get some. So there's always going to be some impurity. Depending on your reaction conditions, the percentage will vary, but a small amount of this secondary will form. But the key thing is this will move over. So if the Cl can attack before it rearranges, or if it rearranges back, rearranges back, which it's always in some sort of dynamic equilibrium. If the Cl happens to time it just right, as the H moves back over and you have a carbocation there, you will end up with a secondary alkyl chloride. The more likely scenario, this H is going to move over. Notice that, and I should emphasize, and I will add this in, this H that moved over, if it was in front, it stays in front. So the orbital electrons must move with the orbitals that it's going to, or move in alignment with. So this H has to be lined up in the plane sticking up and interacting with the empty p orbital sticking up and down. So going out of the plane and into the plane here. So if I were to consider the p orbital, the top p orbital would be right there, the bottom would be in back, and this H would go into that p orbital, that empty p orbital would, so electrons will shift over. Okay, let me get rid of that picture. And so now we have the tertiary carbocation, more stable. It's going to stay like that most of the time. It may, like I mentioned, go back and forth. There might be some equilibrium here, but it's going to favor the tertiary over the secondary. The chlorine's going to then attack, and you're going to with a tertiary chloride species. This is going to be your major product, it's going to be your minor product, but anytime I have H plus and an alkene, I will have to consider rearrangement. And again, just have to remember your carbocation stability. As mentioned, tertiary beats secondary, secondary beats primary. Methyl is just so bad, it just isn't going to exist. You'd have to do something extreme to get it. And then also keep in mind, resonance helps stabilize carbocations. So for instance, a primary resonance stabilized carbocation would beat a secondary without resonance. So consider tertiary over secondary over primary over methyl, and then also consider resonance over non-resonance. Okay, so secondary carbocation, tertiary carbocation. So it's going to rearrange preferentially to form this structure, tertiary. Okay, and then again, as mentioned, resonance stabilizes it more than non-resonance. So resonance that you can get is next to double bond, it's free to move over. So this double bond can migrate over, stabilize the carbocation. So this is called allylic. It's down the alley from the double bond. If it happens to be a double bond in a benzene ring, we call it benzylic, very similar. So benzyl cation, allocation, it's similar in that, again, it can move over, form the pi bond there, and leave the carbocation in this spot so it's free to move around. And then the third type is carbocation next to something with a lone pair. So we can get this species. So carbocation, again, tertiary beats secondary, secondary beats primary, primary beats methyl, resonance beats non-resonance. Okay, so because we have this issue with rearrangement, we have a workaround in chemistry. So rather than adding HCl and have the risk of it rearranging, so as mentioned in that previous example, H is going to go on here, let's say if I did HCl. So let's say I did some HCl or H plus reaction. H would go on there, get a tertiary carbocation, no worries about rearrangement. But if you are worried about rearrangement, and you should, there's always going to be some rearrangement that could occur, then instead of adding H plus, we're going to add something called mercury acetate. And this compound right here, H is in a plus, or Hg is in a +2 oxidation state. One of the OACs will come off and it just becomes a positive. And so what will happen is instead of attacking an H plus, it's going to attack a mercury with a plus charge. So mercury with only one acetate. Notice there's two here, now there's only one. And that's because OAC is going off just by itself, an OAC minus, that's going to balance out the H coming off the water. So the acidic water H is going to form a bond to the other OAC here. So that's your side product. So from here to here, there's also an HOAC, mild acid like acetic acid. And then we're going to reduce it down. And as mentioned in previous podcast, this compound's rich in H. Rich in H makes it a hydride. Hydrides are reducing agents. So it's something that hopefully you recall from GChem if your GChem instructor covered it. Okay, so HGOAC plus. So the plus charge is actually located on the mercury. I've drawn it for formula reasons, but if you want to be more precise, you put the positive charge on the mercury, not on the AC end, and that'll go on first, and it chooses, just like H did when it went on first, the less crowded carbon. So it's going to go on to the secondary carbon. It leaves the carbocation on the tertiary, and so OH is going to go on second, and as we've learned, second thing on defaults to the more crowded or less favorable site. So regioselective, absolutely. The OH, that group we're interested in, is ending up on the more substituted carbon. So it is a Markovnikov addition in the end. Notice H goes where H is, one H here, no H is here. H ended up on the side with more H's. And then OH or whatever group, but in this case, the OH is going on the more substitute. So it's Markovnikov in nature. Stereoselectivity, as always, I have to consider how these things coordinate. The one thing to get into with this mechanism is this Hg can actually coordinate to both. So it bonds to this carbon, but it coordinates to this other side. In doing so, it forces the OH to push it out from the opposite side. That said, it's free to add to either side. So there won't necessarily be stereoselectivity in this because we don't generate a new chiral center. But if there is the potential for a chiral center, then yes, we would have to consider it. But in this specific reaction, no chiral centers, so no stereoselectivity to evaluate. So Hg coordinates the more crowded, which disables the rearrangement. So what this means is, and I'll show it in the intermediate on the next slide, but when it goes on, Hg forms a bond to the carbon, but it also forms what's known as coordination site. So it coordinates the carbocation. So the carbocation I have formed here is coordinated to this Hg. So the plus charge is actually shared between this carbon and this Hg, this mercury atom. So by holding it in place, it prevents this plus charge from migrating around because it's already tied into or has electrons from the Hg tied into it. Okay, so BH4 minus, borohydride as it's called, sodium borohydride specifically, but borohydride will reduce the mercury. It'll put an H onto the carbon, and in doing so, kick out the HgOAC. Okay, so let's look at the reaction mechanism. The reaction is known as oxymercuration because you're using mercury to add an oxygen atom to the compound. So, like mentioned, it's HgOAC2 to begin with. That's a stable structure because it's Hg2 plus and two OAC minuses to make a neutral compound. But when one of the OACs goes away, overall it becomes a positive. So it's going to go and attack just like it attacks an H plus. Again, it can coordinate. This Hg, I want to emphasize, it is free, has lots and lots of electrons. So it can coordinate. So this is the drawing I was trying to show on the other page, where instead of having a full carbocation here, it is partially located on the Hg and the carbon. It is shared. Because of this sharing, there's no reason for this to migrate over because it would create a fifth bond to this carbon. It's not going to happen, so you're not going to have rearrangement. H won't move over for the same reason. So it coordinates it and holds it in place so the carbocation can only be attacked there. Okay, this is where, in this case, we use water. Water can attack this carbon. It's going to go from the backside of the coordinated line. So how it arranges with the stereochemistry here, if it is the stereocenter, you have to evaluate at the time. We don't have a stereocenter coming in, so we don't care for now, but it has come in from the backside, similar to an SN2 reaction to break that coordinated species. You now have a plus charge here, so we got to make sure plus charge started out on this molecule. It's now here. It's now shared. It's now back to being on a single atom. And then if it works out, those electrons can drop off to the oxygen. So they go to the oxygen, and we end up regenerating an H plus somewhere else. Okay, so this is step one. We've added an OH to the more substituted carbon. We have an HgOAC. We need to get rid of the HgOAC, and that's where the sodium borohydride comes in. So I'm going to draw the sodium borohydride as just a source of H minus. That H minus is going to come in and kick out that H2OAC. There's a little more to the mechanism than that, but I'll just say that's essentially what's happening. Again, because it's not a chiral center, I don't care. Okay, we started a spider chart from before. I'm actually going to, for the alkene reactions, end up with two spider charts because we just have too many reactions. So one of the spider charts is going to have reactions at 12 o'clock, 1:33, 4:36, 7:39, and 10:30. If it went too fast, I just described 8 reactions starting from the center compound. We have more than 8 reactions that alkenes can do. So I'm going to actually add in second spider chart. So we're actually starting a second one. Same molecule I was using in the previous one. In the previous one, we added H2O with acid. We saw added Markovnikov. We used HX, HCl or HBr specifically, and it also went Markovnikov. So this one, I want to emphasize we use this to get an anti-Markovnikov reaction. I'm sorry, my apologies, Markovnikov reaction, but also probably want to make a little note, avoids rearrangement. So the reason we do this is it avoids issues with rearrangement. It coordinates the intermediate so that you don't get that issue. Okay, so Markovnikov addition, H goes where H is, so H goes on here, and the OH is left on the more substituted carbon. Okay, that covers one reaction. We spent a lot of time, but really want to emphasize that that's what we're going to have to do for every reaction. Know the mechanism behind it, and the more you understand the mechanism, the more you can make sense out of the reactivity. So with that in mind, I'm going to call it a podcast, and I will see you at the next one. So until then, have a great day. Bye.